Hello everyone, myself is Dr. Khatua. I am an assistant professor in the Department of Chemistry, YS Palpada Mahavidyalaya, Palpada, West Bengal. In this lecture, we are going to discuss about the historical development of quantum mechanics. After attending this lecture, we shall be able to learn about the drawbacks of classical theory which ultimately led to the development of quantum mechanics. The main objectives of this lecture are as follows: to identify the drawbacks of classical theory, to learn about those particular experiments which could not be explained by classical theory, details of blackbody radiation, Wien's displacement law, Wien's equation, Rayleigh-Jeans equation, and of course Planck equation. The drawbacks of classical theory. Towards the end of 19th century, scientists felt that probably all the principles of physics has been discovered. During this time, the scientific community witnessed the development of electricity, magnetism, thermodynamic principles, etc. Nowadays, these are called classical physics. Classical physics primarily deals with macroscopic particles which obey Newton's laws of motion, but by the end of 19th century it was discovered that a few very simple experiments could not be explained by the existing laws of classical physics. These are blackbody radiation, photoelectric effect, Compton effect, and atomic spectra. A closer inspection of these experiments revealed that the laws of classical physics are not applicable to the subatomic particles. So, there was a need to develop a new set of laws that can be applied to the subatomic particles. This ultimately led to the development of quantum mechanics. Let us now have a brief discussion about those experiments which could not be explained by the classical physics. First of all, the blackbody radiation. This curve shows the plot of intensity of a blackbody radiation as a function of wavelength at several different temperatures. The main characteristic features of the blackbody radiations are as follows. Number one, the intensity and distribution of blackbody radiations are independent of shape, size, and nature of the cavity. Number two, at a given temperature, the energy distribution in the radiation spectrum is not uniform. The intensity of radiations first increases with increase in wavelength, reaches a maximum at a particular wavelength which is known as lambda max, and then starts to decrease. Number 3, the Wien's displacement law. According to this law, lambda max is inversely proportional to the absolute temperature. Thus, with increase in temperature, lambda max shifts towards the shorter wavelength region of the spectrum. Mathematically, this is expressed as lambda max proportional to 1 by T, that is lambda max into T equal to constant. Number 4, Stephen-Boltzmann law. According to this law, the total energy emitted by a blackbody per unit area per unit time is proportional to the fourth power of absolute temperature. The total energy emitted at a particular temperature is represented by the area under the curve. So, mathematically, this law is expressed as E equal to sigma t to the power 4, where sigma is called the Stephen-Boltzmann constant and its value is 5.67 into 10 to the power minus 8 joule per meter square per second Kelvin to the power minus 4. Next, the theoretical attempts to construct the spectra. Many theoretical physicists tried to derive expressions that would be consistent with the experimental curves of intensity versus frequency or wavelength. Three main attempts are as follows. First of all, Wayne's equation. Wayne assumed that a black body is composed of vibrating particles that can emit radiation energy according to Maxwell's theory of electromagnetic radiations. Wayne theoretically deduced that the energy emitted, that is E lambda d lambda, by a black body at a certain temperature T within the wavelength region of lambda and lambda plus d lambda is given by E lambda d lambda equal to A by lambda to the power 5 into e to the power minus b by lambda t into d lambda, where A and B are constants. Using this equation, a spectral distribution curve was made theoretically which fits with the experimental curve in the low wavelength region only. Next came Rayleigh-Jeans equation. The number of modes of oscillation, that is dn, per unit volume of the cavity of the black body within the wavelength region of lambda and lambda plus d lambda is given by dn equal to 8 pi by lambda to the power 4 into d lambda. Again, according to law of equipartition of energy, each mode of vibration has an average energy of kT, that is half kT for potential energy and half kT for kinetic energy. Hence, the energy density in this wavelength region is given by E lambda d lambda equal to dn into kT. Now, putting the value of dn in this equation, we can finally derive that E lambda d lambda equal to 8 pi kT by lambda to the power 4 into d lambda. This is known as Rayleigh-Jeans equation. This equation fits well with the experimental curve in the high wavelength region of the spectrum, but fails completely in the low wavelength region. According to Rayleigh-Jeans equation, as lambda tends to 0, E lambda tends to infinity, but experimental results show that as lambda tends to 0, E lambda also tends to 0. This is known as ultraviolet catastrophe. Then came Planck equation. The failure of Rayleigh-Jeans formula in the low wavelength region of the spectrum indicates that there is some drawbacks of the principle of equipartition of energy. Then Max Planck in the year 1900 put forward some bold new postulates regarding the nature of the linear harmonic oscillators, which are as follows. Number 1. The oscillators of the black body cannot have any amount of energy. They have discrete energies which are integral multiples of some minimum energy, that is epsilon 0, such that epsilon 0 equal to h nu, where nu is the frequency of the oscillator. Thus, the oscillators can have the following energies only: epsilon equal to n epsilon 0, that is equal to nh nu, where n is any integer. Number 2. The oscillators can absorb energy only when the energy of the photon is equal to the possible energy change of the oscillator. Based on the idea of quantization of energy of the oscillators, Planck derived the radiation formula as E lambda d lambda equal to 8 pi hc divided by lambda to the power 5 into e to the power hc by lambda kt minus 1 into d lambda. This is known as Planck's radiation formula. It can successfully explain the entire spectrum. Conclusion. In this lecture, we discussed about the drawbacks of classical theory and the historical development of quantum mechanics. We discussed about the blackbody radiation and its characteristic features in detail. Then we discussed about the theoretical attempts by various scientists to construct the blackbody spectrum. Finally, we saw that Wayne's equation and Rayleigh-Jeans equation were successful in explaining the lower and higher wavelength region of the spectrum only, whereas Planck's equation was successful in explaining the entire spectrum. Thank you.